Welcome to the study of a man whose obsession with measurement changed our world. This slide reveals how an eccentric 18th century aristocrat achieved the impossible, weighing the earth. Using the torsion balance illustrated here, he measured the gravitational force between lead spheres to calculate the mass of the earth. By measuring the angle of twist and the torsion constant, he applied the fundamental gravitational law with unprecedented accuracy. His genius extended to decoding the atmosphere, yet he was so reclusive that a century's worth of physics remained hidden in his desk drawer, waiting to be discovered. Meet Henry Cavendish, a man defined by a striking paradox, the scientific ascetic. Though born into high aristocracy as the grandson of a duke and possessing the largest fortune of any scientist in history, Cavendish shunned the world of status. He was a radical recluse who spoke to only one person at a time and communicated with female staff solely through written notes. His commitment to his work was so absolute that he installed back staircases to avoid human interaction and converted his formal drawing room into a laboratory forge. Ultimately, he lived as the richest of all savants, a man who held the keys to a vast fortune but sought only the quiet, solitary pursuit of precision. Henry Cavendish rejected qualitative philosophy in favor of a unifying theory, that the entire physical world could be decoded through exact mathematical relationships and extreme precision. This blueprint of his laboratory work bridges three distinct realms. At the microscopic level, he explored pneumatic chemistry and the composition of gases. Moving to the human scale, he quantified electricity, resistance, and circuit potential. Finally, at the planetary scale, his calculations tackled universal gravitation and density, modeled by the Cavendish density equation, whether examining a molecule or a planet. Quantitative precision was the master key to nature's secrets. To step into Cavendish's world, we must first translate the vocabulary of the 18th century laboratory. This guide acts as a scientific Rosetta Stone, mapping archaic terms to their modern equivalents. Inflammable air is revealed as hydrogen, while dephlogisticated air identifies the oxygen responsible for combustion. The inert phlogisticated air and exhaled fixed air are recognized today as nitrogen and carbon dioxide, respectively. Even the degree of electrification finds a home in modern physics as voltage, the pressure of the electric fluid. By bridging these eras, we decode how early quantitative precision transformed mysterious airs into the foundational elements of our current scientific understanding. In 1766, Henry Cavendish achieved a milestone in pneumatic chemistry by systematically isolating inflammable air, known today as hydrogen. While others had observed gases, Cavendish's pursuit of precision led him to dissolve metals like zinc, iron, or tin in acid to capture the resulting vapors. By weighing the captured gas with meticulous care, he proved it was nearly 9,000 times lighter than water and a mere 1/14 the weight of common air. This elegant experiment, part of his blueprint of precision, didn't just identify a new substance, it quantified the lightest element in the universe, setting a new standard for the quantitative rigors of the modern laboratory. By 1781, Henry Cavendish shattered the ancient belief that water was a fundamental, indivisible element. In a masterclass of quantitative precision, he combined 2 volumes of hydrogen with 1 volume of oxygen, triggering their union with a single electric spark. The result was revolutionary. The gases vanished entirely, leaving behind a weight of pure water, or dew, exactly equal to the mass of the gases consumed. This wasn't merely a successful experiment. It was the definitive proof that water is a compound. Through this blueprint of precision, Cavendish transformed our fundamental understanding of one of nature's most essential substances. In 1785, Henry Cavendish turned his meticulous attention to the atmosphere, using an electric spark eudiometer to systematically remove oxygen and nitrogen. After accounting for the 79.1% nitrogen and 20.8% oxygen displayed in our chart, he discovered a minute, unreactive residue, the 1/120th slice, that stubbornly refused to burn. Cavendish recorded that this mystery gas constituted no more than 1/120th of the nitrogen volume. His measurement was so remarkably precise that it took a century for Rayleigh and Ramsay to identify this residue as the noble gas argon in the 1890s. Through this argon anomaly, Cavendish's quantitative rigors successfully captured a hidden element long before science had a name for it. To silence skeptics who believed the torpedo rays shock was a biological trick, Henry Cavendish turned to engineering. Naturalists doubted the fish's electrical nature because it produced neither spark nor sound. In response, Cavendish meticulously constructed a mechanical proxy using leather, wood, and pewter, powering it with Leyden jars soaked in salt water. This artificial torpedo successfully duplicated the creature's jolt, proving that electricity can manifest as a low-intensity, high-quantity force without a visible discharge. Cavendish's ingenious model bridged biology and physics, demonstrating that nature's elusive mysteries are governed by rigid, quantifiable laws. In a world without the galvanometer, Henry Cavendish turned his own nervous system into a precision instrument. To quantify electrical current, he used his hands to complete circuits, gauging the flow by how far the pain radiated up his arms, whether it stopped at the fingers, wrists, or elbows. This daring protocol of self-electrocution led to a monumental discovery, the resistance of salt solutions. More impressively, he realized that electrical potential is proportional to current. By measuring the pressure of the electric fluid through his own body, Cavendish anticipated Ohm's law decades before George Ohm himself. It stands as a testament to his blueprint of precision, proving that for a scientist this dedicated, even physical pain was a measurable data point. In this installment of The Dawn of Reason, we witness Henry Cavendish undertaking the monumental task of weighing the world. In 1797, using a modified torsion balance originally designed by John Michell, he sought to measure the incredibly faint gravitational pull between lead spheres, a force just 1/50,000,000th of their weight. The apparatus featured 348-pound stationary spheres and 1.61-pound suspended spheres on a delicate wire. To eliminate air currents, Cavendish observed a tiny 16/100th of an inch deflection through a telescope from a separate room. This meticulous approach yielded a calculated density for Earth 5.48 times that of water, within 1% of the modern value. By quantifying this elusive force, Cavendish validated Newton's law of universal gravitation on a terrestrial scale. In this chapter of The Dawn of Reason, Henry Cavendish boldly defies the prevailing caloric consensus of his era. Rejecting the idea of heat as a physical substance, he champions the mechanical theory, arguing that heat is merely the internal motion of particles. By quantifying this agitation as vis viva, or mechanical work, he mathematically bridged the gap between temperature and velocity. Cavendish calculated that particle velocity at 1000 degrees Celsius is double that at 0 degrees Celsius, estimating an average speed of 6,800 inches per second. For the architect of precision, even the invisible vibration of matter was just another data point waiting to be mastered in his laboratory. When Henry Cavendish passed away in 1810, he left behind vast wealth and a reputation for extreme precision, yet his most significant contributions lay hidden in stacks of unpublished notebooks. It wasn't until 1879 that James Clerk Maxwell dedicated 5 years to editing these papers, unveiling a shocking truth. Cavendish was secretly a century ahead of his peers in electrical theory, having already explored complex circuits and fundamental relationships like V equals I times R. This posthumous reveal transformed our understanding of the reclusive aristocrat, proving that while he withdrew from society, his mind was busy mapping the future of physics from the solitude of his desk drawer. Enter the hidden genius matrix, a staggering chronicle of what might have been. This table exposes how Henry Cavendish lived decades ahead of his contemporaries, uncovering fundamental laws of physics that remained locked in his drawers. By 1781, he understood the relationship between potential and current, nearly 50 years before George Ohm's official discovery. He mapped the inverse square law of electric force in 1771, predating Coulomb by 14 years. Remarkably, his 1770s research into parallel currents and dielectric constants anticipated the work of Wheatstone and Faraday by over 60 years. This matrix isn't just a timeline, it's a testament to a man who saw the future of science long before the world was ready to hear it. In 1871, William Cavendish, the 7th Duke of Devonshire, endowed the University of Cambridge with £6,300 to found a laboratory for experimental physics. This facility, named the Cavendish Laboratory, opened in 1874 with James Clerk Maxwell serving as its inaugural professor. The institution quickly rose to prominence as the global epicenter for experimental physics. By producing dozens of Nobel laureates, the laboratory established an enduring legacy that cemented the Cavendish name in scientific history. In the quiet corners of his laboratory, Henry Cavendish forged an unsurpassed standard of precision. He proved that the universe's most elusive mysteries, the composition of the air, the electricity pulsing through nerves, and the gravitational pull of mountains, could be brought into the light through obsessive, uncompromising measurement. For Cavendish, science was not a path to prestige, but a rigorous hunt for the tangible. He shunned the spotlight of fame to labor in the shadows, driven by a singular, persistent goal. He did not seek acclaim, but rather the exact weight of truth.